very much. My behind-the-scenes title at Spotify is Site Reliability Engineer. So we're always trying to think on our feet during incidents and stuff. So I figured, why not? Run up on stage and do a talk 3 hours before I'm actually ready for it. Okay, so yeah, my name is Lynn Root. As Frank said, I'm a staff engineer at Spotify. I've been there for about 6 years. And since the beginning of this year, I've been more focused on building machine learning infrastructure for engineers and researchers that need to productionize their digital signal processing models. So it's super amazing stuff, and if anyone here uses Apache Beam or works with streaming data pipelines, I would love to chat with you. I'm also Spotify's FOSS evangelist. I help a lot of teams release projects and tools under the Spotify GitHub, as well as contribute back to projects. And then lastly, I've helped lead PyLadies, the global mentorship group for women and friends, to help increase diversity in the Python community. All right, getting straight to it. This is going to be a quick talk because I have a lot of material. I'm going to try and fit in half an hour. So yes, async IO, it's the new hot thing, right? The concurrent Python programmer's dream. Answer to everyone's asynchronous prayers. So with the async IO module, it has various layers of abstraction, allowing developers as much control as they need and are comfortable with. Simple hello world-like examples show how easy it is to make something async. It's super simple. But we kind of get lulled into this false sense of security. And this kind of example isn't that helpful. We're made to believe that we can do a lot with the structured async and await API layer. Some tutorials, while great for the developer getting their toes wet, try to illustrate real-world examples. But they're, real-world examples, but they're just beefed-up hello world examples. Some even misuse parts of async IO's interface, allowing one to easily fall into the depths of callback hell. And there are some tutorials that get you up and running pretty easily with async IO, but then you realize that it's not exactly correct or not exactly what you want, or only gets you part of the way there. While some tutorials and walkthroughs do a lot to improve upon the basic hello world, it's still just a web crawler. And I'm not sure about others, but I'm not building web crawlers at Spotify. Sure, I have to build services that make a lot of HTTP requests that should be non-blocking, but these services of mine also need to react from events from a pub sub. And we need to measure progress of actions initiated from these events, handle any incomplete actions or external errors, deal with pub sub messages, lease management, measure service level indicators, and then send metrics. And and I also need to use non-async IO friendly dependencies. So for me, this problem got difficult quickly. So allow me to provide you with a real-world example that actually comes from the real world. Has anyone heard of Netflix's Chaos Monkey? Okay, I see some hands. So at Spotify, we built something similar to Chaos Monkey. We basically create chaos. We have a service creating chaos among all of our backend services, where we periodically do hard restarts of our entire fleet of instances. And so we're going to do the same thing here. We're going to build a service called mayhem mandrill, where we're going to listen for a pub sub message and restart the host based off of that message. And as we build the service, I'll point out some best practices that I may or may not have realized when I first used async IO. And this will essentially become a resource that past Lynn would have wanted about 3 years ago. All the code, the slides, the whole little write-up is on this link right here, so you can just sit back and listen. All right, getting to it. We'll start with some foundational code. We're going to write a simple publisher. And so we have a while true loop with a unique ID for each message to publish to our queue. And I want to highlight that we're not going to use await on queue.put for a message. Async.io.createTask will actually schedule the coroutine on the loop without blocking the rest of this for loop. The create task method does return a task, but we can also essentially use it as a fire and forget mechanism. So if we added an await here, everything after this within this publish coroutine will be blocked. And this isn't really an issue for our current setup. It could be if we limited the size of our queue, then the await will be waiting on space to free up in the queue. So we're just going to stick with asyncio.createTask. And so now that we have a publisher coroutine function, now we're going to make a consumer coroutine function. Here are consumer for the messages that we've published. It's sort of similar to the publisher. We will still have a while true loop, and we await on the queue for a message. But we wouldn't want to create a task out of queue.get. It makes sense to block the rest of the coroutine on this because we can't do much if there's no messages to consume. I want to highlight again that we're only blocking within the scope of the consume coroutine. We're not actually blocking the event loop. So let's replace asyncio.sleep with a function that will restart a host. I'm sure it looks like I'm just pushing the simulated I/O work into a restart host function. But in doing so, I'm actually able to create a task out of it, and therefore not block on consuming more messages. We may want to do more than one thing per message. Like, for example, in addition to restarting a host, we may want to store the message in a database for potential replaying later on. So we'll make use of asyncio.createTask again for the save coroutine to be scheduled on a loop, basically checking it over to the loop to be executed when it can next. So in this example, the two tasks of restarting and saving don't need to depend on one another, completely sidestepping the potential concern or complexity of should we restart a host if we fail to save a message to the database and vice versa, just kind of skipping that part. But maybe you want your work to happen serially. You may not want to have concurrency for some asynchronous tasks. So for instance, maybe you want to restart hosts that have an uptime of more than 7 days. So just like in banking, you should check the balance of the account before you debit it. So needing code to be serial, to have steps or dependencies, doesn't mean that you can't be asynchronous. The await last restart date will yield to the loop, but that doesn't mean that restart host will be the next thing in that loop. It just allows other things outside of the coroutine to happen. So with that in mind, I'll just put all this message-related logic into a separate coroutine, so we don't have to block the consumption of messages. And then saving a message shouldn't block a restart of a host if needed, so we'll just return that to being a task. And we're just going to remove the uptime check and restart hosts indiscriminately, because why not? All right, so we've pulled messages from a queue, and we've fanned out work based off of that message. Now we might need to perform any finalization work off of that message. Often in pub/sub technologies, if you don't acknowledge a message within a predefined time frame, it will get redelivered. So for a finalization task, we should acknowledge the message so it isn't redelivered to us. So we currently have two separate tasks, save and restart, and we want to make sure that both are done before the message is cleaned up. And we could go back to the sequential awaits, since that is a very direct way to manipulate ordering. But we can also use callbacks on a completed task. What we therefore want is to somehow have a task that wraps around the two coroutines, the save and the restart, since we have to wait for both to finish before cleaning up. We can make use of asyncio.gather, which returns a future-like object, which we can then attach a callback of cleanup via the add done callback. We can now just await that future to kick off the save and restart host coroutines. And obviously, the callback of cleanup will be called once those two are done. So you see here that when we run, we see both the save coroutine and the restart coroutine are complete, and then the cleanup will be called that signifies a message being completely done. And we've still maintained appropriate concurrency. However, I personally have an allergy to callbacks. And perhaps we need cleanup to be non-blocking as well. So then here we can just await clean after gather, since the order of operations do matter. And you can see how much cleaner this actually is. So quick review, async IO, it's kind of pretty easy to use initially, but it doesn't automatically mean that you're doing it correctly. You can't just throw around async and await keywords around blocking code. It's sort of a shift in the mental paradigm, both with needing to think of what work can be farmed out and let it do its thing, as well as what dependencies there are and where your code might still need to be sequential. And so having your code, like having steps within your code, like having the first A and then B and then C, might seem like it's blocking when it's actually not. Sequential code can still be asynchronous. I might have to call like customer service for something and wait to be taken off hold to talk to them. But while I wait, I can put my phone on speaker and pet my super needy cat and do whatever else I need to do. So I might be like single-threaded as a person, but I can multitask like CPUs. All right, so often you might want your host or your service to gracefully shut down if it receives a signal of some sort, like clean up open database connections, stop consuming messages, finish responding to current requests while not accepting new requests. So if we happen to restart our own instance of our own like mayhem mandrill service, we should clean ourselves up as well. So here's some typical boilerplate to get a service running. We have a queue instance, setting up a loop, scheduling the publish and consume tasks, and starting and closing the event loop. So maybe you even catch the commonly known keyboard interrupt exception. So if we run it as is and give it the SIGINT signal, we can see that the accept and finally block within those two log lines. But if we send our program a signal other than SIGINT, like sigterm, we don't actually reach that finally clause. So we should be seeing like a log message where we're cleaning up and closing the loop. It should also be pointed out that even if we're only ever to expect a keyboard interrupt or SIGINT signal, that it could happen outside of catching that exception, potentially causing the service to end up in an incomplete or otherwise unknown state. So instead of catching keyboard interrupt, let's actually attach a signal handler to the loop. We'll define a shutdown coroutine that will be responsible for doing all of our necessary shutdown tasks. Here I'm just closing simulated database connections, returning messages to PubSub as not acknowledged so they can be redelivered eventually and not dropped. And then collecting all of outstanding tasks except for the shutdown task itself and canceling them. We don't necessarily need to cancel pending tasks. We could just collect and allow them to finish. And then we might also want to take the opportunity to flush any collected metrics so that they're not lost. So then let's add our shutdown coroutine to the event loop. So the first thing is we set up our loop and then add signal handler, add our signal handler to the loop with our desired signals that we want to respond to. And then we can also remove the keyboard interrupt catch. So then running this again, we see that we do actually get to that finally clause with something other than SIGINT. Now you might be wondering which signals to react to. What should you actually care about? And apparently there is no standard. Basically, you should be aware of how you're running your service and handle it accordingly. And it seems like it can be quite messy with conflicting signals, particularly with adding Docker into the mix. So we don't have like nurseries in async IO core to clean ourselves up, and so it's up to us to be responsible and close up connections and files, respond to outstanding requests, and basically leave things how we found them. Doing our cleanup in a finally clause isn't enough, though, since the signal could be sent outside of a try except clause. And so as we construct the loop, we should tell it how it should be deconstructed as soon as possible in the program. We need to also be aware of when our program shuts down or should shut down. It should be closely tied to how we run our program. So if it's a manual script, maybe sigint is fine, but if it's daemonized within a Docker container, then sigterm might be more appropriate. I don't have enough time to go into it, but if you need to use async.io's shield to kind of shield your task from cancellation, be aware that it doesn't necessarily respect shutdown behavior with the signal handler. So just be aware. Moving on to exception handling. You might have noticed that we haven't really handled any exceptions so far. We're going to revisit our restart host coroutine and add a super realistic exception. So when running this, we do see that there is that super serious exception raised. But we also get a task exception was never retrieved. We don't properly handle the result of a task when it raises. What we can do is define an exception handler and then attach it to our loop, similar to signal handling. So then when we're rerunning this, we see that the logging of the exception actually happens. So we've set exception handling on a global level, but perhaps you want to treat some exceptions for certain tasks differently. And we're going to revisit our handle message coroutine. So say, for instance, you're fine with logging when save a message fails, but you want to knack or not acknowledge the pub/sub message and put it back in the queue if restarting a host fails or something like that. So since asyncio.gather returns results, we can add a more fine-grained exception handler based off of that and handle results as we wish. Now I want to highlight that setting return exceptions to true for asyncio.gather is super imperative. Otherwise, exceptions will be handled by the default handler if it's set. And if there's no default handler set, then it just kind of gets swallowed up and sort of blocks itself. And it's kind of hidden because the service will otherwise keep running. So a quick review over exception handling. Be sure to set some sort of exception handling, either globally, individually, or a mix. Otherwise, exceptions will go unnoticed and can cause weird behavior. I personally like using asyncio.gather because the order of returned results are deterministic, but it's easy to get tripped up with it. So by default, it will swallow exceptions, but happily continue working on other tasks that it was given. So if an exception was never returned, then the weird behavior will happen. All right. So sometimes you need to work with threads, like a threaded pub/sub client. Maybe you want to consume a message on one thread and handle the message within your coroutine in the main event loop, which is a separate thread. Let's first attempt to use the async.io API that we're familiar with and update our synchronous callback function with creating a task via async.io.createTask from the handle message coroutine we defined earlier. We'll then call our threaded consume function via a thread pool executor, much like how we would treat synchronous code. But we don't actually get that far. At this point, we're in another thread, and there's no loop running in that thread, only in the main thread. Okay? So if we take what we have right now and then update our functions to use the main event loop, it looks like it works, right? But it's actually deceptive. We're kind of lucky that it works. So in an effort to save time, I'm just going to tell you that we're not being thread safe. So instead of loop.createTask, we should be using async.io's thread-safe API. The run, and specifically the run coroutine thread-safe method. And it can be difficult to tell when you're not being thread-safe if you are in a multi-thread environment, particularly when it looks like it does work. as it did previously. But later on, I'll show you how easy it is to surface the issue of thread safety. All right, so in my opinion, it's not too difficult to work with threaded code with async I/O. Similarly to how we work with non-async code in an async world, we make use of a thread pool executor, which essentially creates an awaitable for us. However, it is difficult to work with threads in async I/O, particularly when sharing state between threads in the main event loop. So if you must, use the thread-safe APIs that async I/O gives you. And it did take me an embarrassingly long time to figure out that I needed this. So moving on to testing. So for a more simplistic starting point, I'm going to test async I/O code before we introduce threading. So we'll start simple, testing the save coroutine using pytest. Since save is a coroutine, we need our test to run it in an event loop. So in 3.7, it makes it easy for us to just call asyncio.run. But with older Python versions, we'll have to construct and deconstruct the event loop ourselves. But there is a better way. There is a pytest plugin called pytest async I/O that will essentially do the hard work for you. You'll need to mark particular tasks that are testing asynchronous code with a decorator from the plugin, as well as make it so that the test function itself is actually a coroutine function. So now when running tests, the plugin will essentially do the work for you, constructing and deconstructing the event loop. So the pytest async I/O plugin can get you pretty far, but it doesn't help you when you need to mock out coroutines. So for instance, our save coroutine function calls another coroutine function, the asyncio.sleep, or an actual call to a database. You don't actually want to wait for asyncio.sleep to complete while you're running tests, nor do you actually want to call a database during your tests. In both the unittest.mock and pytest mock libraries do not support asynchronous mocks by nature, so we'll have to kind of work around this. So first, we'll kind of build upon the pytest mock library. We'll first create a pytest fixture that will return a function. And so the outer function itself returns the inner function as a fixture that we'll end up using in our tests. And then the inner function is basically creating and returning a mock object that we will actually use in our test, as well as a stub coroutine that will end up calling our mock. It will also patch, if needed, the desired coroutine with the stub to avoid any network calls or sleeps, et cetera. So now let's create another pytest fixture that will use the create coro mock fixture to mock and patch asyncio.sleep. We don't need the stub coroutine that create coro mock fixture function returns, so we can just throw it away. And now let's use a mock sleep fixture in our test save function. So what we've done here is basically patched asyncio.sleep in our mayhem module with a stub coroutine function. Then we assert that the mocked asyncio.sleep object is called once mayhem.sleep is called. Because we now have a mock object instead of an actual coroutine, we can do anything that's supported with standard mock objects, like assert called once with, or setting return values, side effects, et cetera. So it's pretty simple, like in my point of view, I guess. But you might need to test coroutine functions that call create task. And we can't simply use the create coro mock fixture, however. So for instance, let's revisit our consume coroutine, which creates and schedules a task on the loop out of handle message. We'll first need a couple of fixtures for the queue that gets passed in. So we'll first mock and patch asyncio queue class in our module. We'll then use that mock queue fixture in another one, a mock get fixture. Unlike our mock sleep fixture, we will actually use the stub coroutine that create coro mock returns and set it to the mock queue's get method. So here in our test consume function, what we're giving our newly created fixtures. So now let's try to use create cover mock to mock and patch the call to handle message, coroutine via create task. Let's see. We're setting the side effect to one real value and one exception to make sure we're not permanently stuck in that while true loop. And finally, we want to assert that our mock for handle message has been called after the consume has been run. When running this, we see that mock handle message does not actually get called like we're expecting. This is because scheduled tasks are only scheduled and pending at this point. We sort of need to nudge them along. We do this by collecting all returned tasks, not just the test, not that test itself, and then running them explicitly. This is a little clunky, I know, but if you typically use unit test from the standard library, there's a package called async test that handles this better and exhausts the scheduled task for you. I only have like a few minutes left, and I'm going to skip the testing the event loop, which is covered in the write-up that is linked at the bottom. And I want to go directly to debugging. All right, so we're decent programmers, right? And we have our good test coverage, but sometimes shit breaks, and we need to figure out what's going on. So we're going to use everyone's favorite debugger. We're going to print everything, sort of, I guess. So if you only have like one small thing to debug, you can use print stack method on a task instance. So when running this, it will print the stack for each running task. And you can also increase the number of frames that are printed as well. However, there's a more proper debugging method. Async.io has a debug mode already built in the standard library itself. So along with setting our logging level to debug, we can easily turn on Async.io's debug mode when we're running our script. If we didn't have a proper exception handling set up, we'd get information about which task was affected, but we also get a source traceback to give us more context, in addition to our normal traceback. So without the debug mode, we get told that there is an exception that's not properly handled, but the debug mode gives us additional clues of where they might be. Another handy thing, as I referred to earlier, I wish I knew this a few years ago, is that if you have to have threads and the event loop interacting with each other, debug mode will surface any sort of non-thread safe operation for you. One really nice feature of the debug mode in Async.io is it acts like a tiny little profiler in that it will log asynchronous calls that are slower than 100 milliseconds. So I can show you real quick, like we're going to fake a slow coroutine, and when we run that, we can see that the debug mode will surface slow to finish tasks, potentially highlighting unnecessarily blocking tasks. The default of what's considered slow is 100 milliseconds, but that is configurable as well. You can just set slow callback duration in seconds. So much like some people's testing philosophies, sometimes we want to debug in production. You might not want full debug mode on. So there's a super lightweight package called AIO debug that will log slow callbacks for you. And that's literally the only thing that it does. No extra context or thread safety. Well, I got like 1 minute left. It does come with the ability to report delayed callbacks to statsd as well. So you got print tasks, you got debug mode, and AIO debug. All right, I want to get to profiling. This is the last section. So sometimes you might need to profile. You can start off by C profile. You can't really glean that much, though. The top item here is the event loop itself. If we just look at our own module, we can kind of get a picture of what's going on, but nothing is immediately surfaced. So I recently discovered that kcache grind can be used with Python. So to do so, we must save the output of C profile, and then use a package called pyprof to call tree. That makes the output of C profile and converts the data into something that kcache grind can understand. So when you run that script, you met with this UI. It's OK if you can't really see anything, but basically on the left-hand side, I'm out of time, but on the left-hand side, there's profiling data that you'd otherwise see from cprofile, and then the sections on the right are the call graph and information about callees. I want to highlight that there's also line profiler, so you get a bigger visual with the K-cache grind. Then you can use line profiler to highlight specific lines of code. And then you can see that like logging is kind of slow here. So if you use AIO logger, you can kind of speed that up a bit. And then there's also this live profiling package that I don't have time to go into. And thank you. Sorry.